Hi everyone. In this tutorial we're going to do a quick introduction to Grasshopper's graph mapper functions. We're going to develop some parametric forms using graph mapper and also do some surface tessellations. So let's begin by looking at the graph mapper tool. So I'm going to first plot some examples for you so that we can actually understand how the graph mapper works. So graph mapper is simply located here under parameters graph mapper. Let me show it this way. So that's the symbol. And this is basically, if you right click on it, you have a few graph examples. So we're going to actually start looking at a few of these, but also I have another version of the graph mapper that might be useful for you. But let's actually look at a linear function first so that we can understand how this tool works. So I'm going to do range this time to use for a range of points. So let's say we plot some points along the x-axis. So range is similar to the series function. So in series, if you remember, this is actually incremental. So we have starting value, increment, and a total value, and this gives us total number of points. In range, what is different is we work with bounds, and we set a number of steps for division. So you can actually assign a domain here as well. So if you connect a domain, and if your domain starts from, let's say, going from 0 to 40, and this will be basically subdividing that interval into equal increments. So I can just divide 40 into 20 steps. If I plug this into x, this will be another way of defining the points. So I can actually, you can see here we can subdivide the interval into more number of points. I can also stretch the interval, but this will be the basic use of range. In this case, we work with a domain, and we work with number of steps to divide that domain. So the reason why I'm covering range is because graph mapper is actually working with range as well. So if you recall your basic mathematics, this is basically a mathematical function. So it's working like a graph of x and y functions. So x is simplified by this horizontal axis that goes from 0 to 1. So 0 will be this bottom left corner, 1 will be bottom right corner, and the y-axis is going from 0 to 1 as well. You can double click and enter into the graph mapper, and here you can also see how the points and the values are distributed. So right now the slope is 1, but you can actually parametrically override these values, or you can simply use these handles to change the slope or the line. So we can also change the intervals here. For instance, we can make the graph go from 0 to 5, so you can see that these numbers have changed. The way this works is actually if you supply any value to the graph, let's say I'm supplying 0.25, this line is actually evaluating the intersection of this value, and it's kind of giving me an output, right? So what's happening is at 0.5, this red line is intersecting with our function here, and that's corresponding to some y value in the horizontal dimension. So that's giving us 2.82. So if you change the slope here, you can see that the value is also changing. If I make it horizontal, all the values will be similar to this value here. So we can actually basically use range in a similar way. Since we have the horizontal domain to be between 0 and 1, we can simply divide it into increments as well. So let's say I divide it into 10 increments. Now, rather than supplying one value, I can supply 10 values. Now you can see we have actually 10 red lines drawn. Sometimes if the division is too much, these red lines are not shown because the graph is way too large to visualize it. I mean, way too small to visualize it, so it shows up to like 4 or 5 or 10. But all of these values now have a corresponding y value. So I'm going to actually plot this onto these points. One way of doing that would be to use them directly as our y point. So we have a domain here and a number of divisions, so I'm going to match these to be exactly the same and connect this to y. So you can see now I'm controlling the y value of these points with my graph. If you want to change the increment here, you can multiply it with some more value. Let's say we multiply it by 2. I can also change the y interval here. Actually, let me make it go back to 1 so that it's normalized. Then we can influence it here a bit more. So I'm getting it kind of a coefficient and then changing how the values are plotted. So the maximum value here will be 20. The cool thing about this is you can actually play around with it using different functions and different number of points. So I can actually increase the number of points. I can plot more functions, right? So this is a sign summation function that has 2 signs. And we can actually use this to develop a lot of different shapes, profiles, as well as sections for nice forms. So one way of approaching this would be to use the revolve function. So what I'm going to do is basically I'm going to move this closer to the y, to the x-axis. But let's actually swap these so that we can actually look at it in perspectival view. And what if we have this as the z values this time? I'm going to connect this to z and disconnect y. And what if our y values, actually our x values, let's see, no, we want this to be our x values and we want this to be our z values. Yeah, there you go. So we want the points to go up in the z direction, and we want this graph to actually influence the section in this direction. So I'm going to use this to make an interpolation. So interpolate these points. You can use this, and the degree could be 3. We don't need it to be periodic, which will connect the beginning and the end. And I want to use the revolve function as well. So let's look at revolve, which is revolution. So for revolution to work, we need a profile curve and a revolution axis. So the axis is an empty line parameter, which could be basically a line STL. So a line STL is basically, it can start from the origin, XYZ, and the direction could be Z direction, and you can supply any type of value, let's say 50. It actually doesn't matter, it could be just really short. So this will be our axis, and this will be our profile, and there you have it. So this is giving us the angle domain in radians, but it's also a domain, so I can construct another domain here so that we can look into that. So if we want to start from 0 to, let's say, 180, I can make the interval into radians and supply it here. So this will actually control how much we want to turn. Actually, let me make it 0.360. So if you want full rotation, you can actually rotate this all the way around, or up to 270 degrees. So I'm going to turn off the points, and let's see. Let's actually play around with this a bit. So now we can actually generate a lot of cool forms using the graph mapper. You can also right click here, look at some other graph types. For instance, there's interpolated. This will actually give me a lot of other cool forms, right? So this would, we can also increase the definition, so you can add more points, reduce more points. It's totally up to you. This is actually not taking much difference. There's another way to influence this as well, which is called the rich graph mapper. So let's see where that is. So I also had under math utilities, I loaded this rich graph mapper. So this is kind of a similar tool. If you right click here, there are more interpolated options, so you get more control points basically. It's kind of different than this, but basically you can actually do, you can have input values. The source domain, target domain could be the same. So if I put this in, I can actually use the output of these values. So there you go. So this would actually give me more control points if I wanted. If you want to generate more interesting shapes, you can also right click and increase or reduce the point count, come up with another shape again. All right, I'm gonna keep this as is because what I want to do is just have the graph mapper as a form derivative. So I want to use this to derive the shape, but there are a lot more things we can actually do with this. For instance, we can also do twisting forms using the graph mapper. So let me show you how that works. So I'm going to disable one of these and create a new point, and this point I'm going to create it with the range again. Let's keep working with the range, and let's say this time I'm creating a row of vertical points, but I want to have let's say 10 points. And I'm going to place an ellipsoid into these points. And the radius values, let's create graphs for those. So I'm going to make copies of the graph and keep the range as is, but use the same number of division. And use multiplication here. So that will be kind of the deriver of my graph mapper. So this goes to R1, and I'm going to make another one. This one is going to be R2. And I'm also going to have something else, which is going to be rotation. So let's say rotate. So we can rotate a bunch of things. We can rotate the ellipse, or we can also rotate its plane. So remember that we are drawing geometries onto planes. So what if I place a plane onto these points? So I can actually rotate the plane, rotate planes, and we're going to do in radians this time. So I'm going to make a copy. And let's do 360 degrees and turn it into radians as well. You can also turn this into angles, but we can keep this as is. My plane preview is too much. Let me actually reduce it. So preview plane size, let's make it 20. That's also a bit too much. Let's make it 10. So these are the rotated planes. So if you have, let's say, a line here, if you don't have any rotation, if the rotation value is the same, now all the planes will be facing the same way. But if you want more rotation, then you need kind of a continuous function of rotation. So let's say I'm going to keep it as x equals y, but then we can control the total rotation here. Right, so this will give our form some sort of twist. So I'm going to place this here. Now I'm not only rotating the ellipses, but I'm also controlling their radii. So now if we loft this, the result, we will have a twisting shape. Okay, so now that we have it, actually, you can also control the ellipses here. You can also make it, let's say we use Bezier function. This would actually give us, you can start with a large value and go down a smaller value. And same thing here. It's easier to control this with less values, less points. All right, there's our form emerging. I actually have a real large value here, but a real small value here. So I'm going to increase this a bit more. So let's see, maybe decrease the twist a bit. If you make it 90. This one needs to go up as well. There you go. So it's kind of parametric sculpting basically. I'm not only controlling the radius values, but also the rotations, the twists. So once you have something that you like, you can actually go to this face here. And what I'm going to do is, actually, let me increase this a bit more. Let's see, and decrease this a bit more. That's much better. All right, so what I want to do now is to divide this surface into panels. So to do that, I'm going to do divide domain squared. And I'm going to divide the U and V values into some panels. So this is the surface and this is the domain. So I'm going to basically generate some panels here. And these are facing inward, but we could also make them face outward. That's totally up to you, but let's actually make it -1 ... 1, and let's bake it and see what we have. So that's basically it. These are basically going to be surface panels that we can replicate with some other panel later on. But this is basically generating a parametric form and then basically placing some sort of shape or form here. So 20 and 20, let me explain what I did here. I basically have a surface and I'm dividing it into panels. So we can also see these panels with isotrim. We're going to use these functions a bunch of times. So you can take the surface and the division. So what isotrim and divide domain squared does is it basically, the surface has a grid. We use u and v values to actually understand it. And when we subdivide the u and v into numbers, this is basically dividing the domain of the surface into equal increments. So we can control the number of panels on the surface, like you see here, and we can control the number of panels in the vertical direction as well. So I'm going to keep the vertical direction as 10, horizontal direction as 20. So these will be all the panels that we get on the surface. So we can directly map something onto these panels, but what I'm doing is I'm actually doing surface boxes, which basically generates an offset cage here like this. So we in each individual ones of these has basically a box shape. We call these twisted boxes, and this helps you to morph some geometry or some tile onto these boxes. So basically has, if you turn on the solid points, you will see it has 8 corners like this, and using these 8 corners you can map some other geometry onto this. I'll show you what that does in a second. So basically we can model something here, or you can model something directly here, but since I want to do everything without using Rhino, let's actually try to do it here. What we can do is actually create a rectangle and a rounded rectangle inside and create a surface and then extrude it. So basically you can make a rectangle. Let's actually place this rectangle somewhere here. So XYZ. So let's move it along the x-axis a bit. So there's my panel. So it could be similar to the proportion of our panels. It doesn't have to be, but let's keep it like this. Then I'm going to scale the rectangle down. We can use the area function to get its centroid. So this is the center, this is the rectangle, and I'm going to do it kind of a coefficient, let's say 0.5. Then I'm going to do a fillet. So fillet the sharp corners of a curve. Let's make it 0.3. So this is the inner shape, this is the outer shape, and I want to merge both of them together and do a boundary surface. So this is the surface that we have, and I'm going to do extrude. So I want to extrude this in the Z direction, and that will do actually. So that will be the panel I want to place here. So I'm going to also cap these. So this is the geometry that I want to use. By the way, you can also model this manually and input it to this Grasshopper script, but I'm kind of doing everything in Grasshopper so that you can learn how to use other tools as well. So we have this. Now I can do a bounding box, and this should be a single box. This is my geometry. I'm actually going to create a geometry container here, place this here. So these are my surface boxes. So the tool that we need is called box morph. So what box morph does is it has a geometry that we want to morph, and we have a cage, which is this. So you can see that it's a box. It has 8 reference points, and we have 8 reference points on the surface as well. So what's going to happen is it's going to use this as a reference, and it's going to move these elements onto the surface. So the way to do that would be, this is my geometry, this is my reference box, and my target boxes are here. So let's see if this works. Okay, there we go. So we have placed the boxes on the surface. So let's bake it and see what we have. So it's a bit heavy, but you can see each of these are basically twisted versions of our sample shape, right? So you can actually try doing other shapes as well. And it's kind of turned out really nice, actually. So this would be kind of an introduction to the graph mapper. So you can try actually other types of forms, other types of ways of building shapes. You can also use the revolution and generate a tile like this, and then try to populate it onto the surface using box morph and the surface box component.